Welcome to the video lecture of ECE 3030. So in this lecture we will be continuing our discussion on CMOS inverters. So in this video lecture we will be focusing on the power and energy dissipation in an inverter, and inverter is a model system here. So essentially the ideas about our power and energy dissipation that we develop for inverter, we will later use the same concept to understand the power dissipation in a microprocessor as a whole. So this slide summarizes all the different components of power and energy in a inverter. So the first component of energy or power is what we called active power or dynamic power or switching power or energy. All of we typically use all of these three words to refer to this kind of energy, and this power dissipation or energy dissipation happens due to the charging and discharging of the load capacitor. So we'll talk about it in this lecture. Second component is the static power, and this happens because of the off-state leakage or off-state current or the subthreshold leakage or the subthreshold current in a transistor. So we'll also talk about this one. And the third component of energy and power is those due to the short circuit current in an inverter. So in this lecture we will not talk about the third component, we will talk about only the first component and the second component. Alright, so let's get started with the first component. So this slide we have already seen before while we were talking about delay in a microprocessor, and the idea was that in general a logic blocks are usually cascaded. For example, here we are showing a chain of inverters. So basically the output of one inverter is input to another one. So for example, this inverter, the output of this inverter feeds another inverter, and this circuit wise it looks like this. And what we have seen is that the output actually feeds to another capacitor, and that capacitor is essentially formed by the gate capacitance of the N-type MOSFET and the P-type MOSFET, or the pull down MOSFET and the pull up MOSFET of the second stage. And the input capacitances are denoted by this CL here, or the load capacitance is denoted by CL. And again, this CL is basically the sum of the input capacitances of the N-type MOSFET and the P-type MOSFET. Alright, so again this is what we have seen before. So for example, the input Vi goes from VDD to 0, and as a result the output will go from 0 to V0, and the way this transition of output happens is essentially the process can be thought of as the capacitor CL charging through the resistance RTP, where RTP denotes the effective resistance of the pull up transistor or the P-type MOSFET. And again remember, the N-type MOSFET is open circuit here when your input goes from VDD to 0 or logic level 1 to 0. Alright, so again so the input went from VDD to 0, so the output will go from 0 to all the way to VDD, and as we have seen before, the output voltage rises with a time constant of RTCL. So let's call this time constant as tau rise, tau R equals to RTP CL. Alright, so what we can do is we can simply write V0 equal to VDD multiplied with 1 minus exponential t over tau r. Okay, and also, and so the V output is over here, and from simple RC circuit basics, if the current that is flowing through this branch is IR, which is I rise, then you can also see that I rise IR is simply VDD over RTP exponential E exponential minus t by tau r. So okay, so now if a capacitor is charged from 0 to VDD, what is the energy that is drawn from the power supply voltage VDD? So energy, so if we write energy as E, energy is simply VDD multiplied with IR into dt, and just we can write it as 0 to infinity. So essentially infinity is written for a mathematical convenience, but you can replace this infinity for all practical purposes by something larger than 5 tau r. So now if you simply do this integration, what you will get is VDD squared over RTP and then this integration minus t over tau r dt, and finally what you will get is VDD squared over RTP multiplied with tau r minus e power minus t over tau r. The limit is infinity to 0, and then this one will come out to be CL VDD squared. Now how does it come? Because tau r is RTP CL, so RTP over tau r is simply 1 by CL, so just replace it, you will get this one. Alright, so what does it mean? It means that when the input goes from VDD to 0, the output goes from 0 to 1, and as the capacitor is charged from 0 voltage, starting from 0 voltage to VDD, total amount of energy that gets transferred from the power supply voltage to this capacitor comes out to be CL VDD square. Alright, now note that one of the important thing is that the power supply gives it CL VDD square of amount of energy, but the capacitor, the stored energy in the capacitor is equal to half CL VDD squared. And you might have seen in basic electrical circuits class that although the power supply gives CL VDD amount of energy, only half of it gets stored in the capacitor and half of it is actually lost during this charging process. Alright, so again the total amount of energy that is dissipated to charge this capacitor CL to a voltage of VDD is equal to CL VDD square. Alright, now when the output input goes from 0 to VDD, the output goes from VDD to 0. Now what happens is that this output voltage was initially at VDD voltage, and then during afterwards, this when the input goes from 0 to VDD, all this charge due to this VDD voltage gets discharged through this resistance, through the N MOSFET, or the effective resistance RTN, and as a result the VDD goes from the output voltage, so let's write it, V output goes from VDD to 0, and in this process the half CL/VDD square amount of energy that was stored in this capacitor gets lost through this resistor. So again, when the capacitor charges up to VDD, when your input goes from VDD to 0, total amount of energy that the power supply gives to the capacitor is the total amount of energy that's dissipated from the power supply is CL/VDD square, and out of it half CL/VDD square amount of energy gets transferred to the capacitor. And when the input goes from 0 to VDD, the output goes from VDD to 0, and this half CL/VDD amount of energy that was stored in the capacitor gets lost or gets discharged to this resistor. So if we summarize this, so initially the input was 0, it went up to 1, and then from 1 it went up to 0. So what happens during an entire cycle of entire time period of t, where t is simply the inverse of the clock frequency, the total amount of energy that gets dissipated in the inverter is CL/VDD square, which essentially means that the power supply voltage gives out CL/VDD amount of energy, and after a time period of t, this CL/VDD amount of energy is dissipated in the inverter. All right. So what is the power? So power is essentially defined as the rate of energy dissipation. So this amount of energy dissipated in one cycle, so per unit time, the amount of energy that is dissipated per unit time, which is power, is equal to E over T, and you can simply write, so T is 1 over frequency, so is EF, and you can write it equal to CL VDD squared F. And this equation, this is a very simple equation, but this is very powerful, and this essentially shows that if your frequency goes up or if your clock rate is high, you will dissipate more power. At the same time, if your VDD is high, you will dissipate more power, and also if your CL is low, you will also dissipate small amount of power. Alright, so we have looked into the first component, the active component of the power, or the active component of the energy, and this essentially happens because of the charging and discharging of the load capacitor in an inverter. Next, look at the static power, and as we said, the static power happens due to the off-state current or the off-state leakage or the subthreshold current or the subthreshold leakage. All of these mean the same thing. So again, the same picture here. So the input goes from VDD to 0. So as a result, what happens is that, so when the input voltage becomes 0, the N MOSFET gets into is off, and as a result, previously what we did was we represented it with an open circuit, and as a result the current was the power supply voltage was simply charging up the capacitor, and the output voltage was becoming equal to VDD. Alright, so now if you look at this N MOSFET here, or if you look at this N MOSFET here, when your V input is 0 volts, the output is VDD. This is true for all practical purposes. So essentially what you have gotten is, for this N MOSFET, your VG is equal to 0 and your VDS, so here is the drain voltage, so VDP, your VDS, so this is N, so your VDS for this N MOSFET is equal to VDD. And when we were discussing the subthreshold current, we looked at the off-state current, and we defined off-state current as the current that flows through the device when your drain voltage, or VDS, drain to source voltage, is equal to the power supply voltage and your gate voltage is 0. So this is what we defined as the off current. Now you can clearly see that this is the case for this MOSFET when the input is 0. When the input is 0, your gate voltage is 0 and the drain to source voltage is equal to VDD. So as a result, although when we were analyzing it as an for the purpose of delay, we say that it's an open circuit, actually a small amount of current is actually flowing through this N MOSFET when your input voltage is 0, and this is what we have called as the off current. So this off current is again very small. So for the purpose of analyzing this system for delay calculation, you can still represent this N MOSFET with an open circuit, but for power considerations you should still consider that there is a small amount of current that is flowing through the N MOSFET when the input is 0 or when this N MOSFET is in the cutoff region. So, so what is happening? What is happening is that still a small amount of current is flowing through this device, through the N MOSFET, and when considered the case, say for example beyond this, when your output has stabilized to VDD, so you have a VDD voltage here and this circuit is completely charged, so there is no charging current flowing through this transistor, and as a result if you have a small amount of off current flowing through this N MOSFET, the same amount of current will flow through the P MOSFET as well, and as a result you will get a static power dissipation due to the off current flowing through this circuit, which will be equal to VDD multiplied with I off. And you can clearly see that now you can clearly see what is the effect of the off current. So if your devices, the N MOSFET, has a large off current, you will dissipate a large amount of static current. Note that in this case the circuit is not doing anything, it's not switching, so basically the logic levels are not changing, and even though logic levels are not changing, still you are dissipating this amount of VDDI of amount of current, and because the logic circuit is not doing any computation under this condition when the inputs are not changing, still there is a certain amount of power that gets dissipated in an inverter. Now similarly when the input is equal to VDD, your output is equal to 0 volts in static conditions, and here what you have is that your source to gate voltage for the P MOSFET is 0. On the other hand, the source to drain voltage is equal to VDD, because here the voltage is VDD for V input voltage of VDD, and as a result there will be a small amount of current that will be flowing through, and that is what we have called I off, and the same amount of current will flow through this, and as a result when your input is equal to VDD, you will get the same amount of static current that is equal to VDD multiplied with I off. Alright, so that's that. So there are two components of power and energy dissipation. First one is the active power or the dynamic power or the switching power, and that power is equal to CL VDD square F, that depends on the frequency. On the other hand, static power, and the static power is simply VDD multiplied with I off, and note that the static power is independent of frequency. So that is one important distinction between static power and the active power.